Okay, welcome back everyone to our Calculus 3 class notes. We're on page 79 and we're working into example 73 here, and we want to talk about doing Lagrange multipliers with two constraints. So the problem here is that we're trying to find extreme values of a function of x, y, and z subject to two different constraints. So not just one g equals 0, but g1 equals 0 and g2 equals 0. In this case, what we want to do is we want to find x, y, z, and lambda, but also another scalar mu simultaneously that satisfy the gradient of f is equal to lambda times the gradient of g1 plus mu times the gradient of g2. And then, of course, that g1 and g2 are both equal to 0. So these Lagrange multipliers, now lambda and mu, will allow us to be able to plug into both of our constraints and then figure out what maximizes or minimizes the function f. Okay, so as far as an example 73, the plane x plus y plus z equals 1 cuts the cylinder x squared plus y squared equals 1 in an ellipse. So you can see the plane right here, and then you can see the cylinder, and then you can see that the plane cuts the cylinder in this ellipse right here. So we want to find the points on the ellipse that lie closest to and farthest from the origin. So again, following that same trick where we have the distance from any point x, y, z to the origin, where it's really the square root of x squared plus y squared plus z squared, we can drop that square root and just find the extreme values of f of x, y, z equals x squared plus y squared plus z squared, right? Because this is the distance between any point x, y, z and the origin. So minimizing this is the same as minimizing this. We just make it much easier not having to deal with the square root. Okay, so then subject to g1, which is x squared plus y squared equals 1. So we set it equal to 0, right? X squared plus y squared minus 1 equals 0. So that's the cylinder. And here's the plane, x plus y plus z minus 1 equals 0. So now we set up the problem like this. Gradient of f equals lambda times gradient g1 plus mu times gradient g2. So looking at f, the gradient is 2x, 2y, 2z. The gradient of g1 is 2x, 2y, 0. And the gradient of g2 is 1, 1, 1. So that tells us that 2x is going to equal 2 lambda x plus mu, and 2y is going to equal 2 lambda y plus mu, and 2z is going to equal mu. So right away we know what mu has to be. It has to be equal to 2z. So we take the first two equations and plug in mu for plug in that mu is equal to 2z. So instead of 2x equals 2 lambda x plus mu, we now have that 2x equals 2 lambda x plus 2z. Okay, which I can then get some sort of relationship between x and z. So I got 1 minus lambda x equals z. And then I do the same thing with 2y equals 2 lambda y plus mu. Again, mu is 2z. So I can get another relationship between y and z. 1 minus lambda y equals z. Okay? So what I have is a situation where lambda equals 1. Right? If lambda equals 1, then that would apply that would mean that z has to be 0. That's this case. Or if lambda does not equal 1, then both x and y are z over 1 minus lambda. Case 2. So let's look at case 1 first. If z equals 0, then the two constraints say that x squared plus y squared equals 1. And then x plus y, now remember there was a plus z, but that's 0, equals 1. So that means that y equals 1 minus x. So if I plug that back into the first constraint, I get a situation where x is either 0 or 1, and then y is either 0 or 1. 1 or 0 at the same time. So when x is 0, y is 1. When x is 1, y is 0. So points on the ellipse are 0, 1, 0, and 1, 0, 0 from that case. Okay? All right, and then if the second case, x equals y both equaling z over 1 minus lambda, then the two constraints say that. Okay, so instead of x squared plus x squared equals y squared equals 1, I now have x squared plus x squared because y is equal to x equals 1, which means that x equals plus or minus 1 over root 2 or plus or minus root 2 over 2 if you rationalize the denominator. It's not that important to do, but I did it in this case. And then for the plane, I have x plus y, but that's now x plus z equals 1. So I get x, which is the square root of 1 over 2, or square root of 2 over 2. So 2x is plus or minus the square root of 2, plus z equals 1. So z equals 1 minus plus square root of 2. Okay, I'm going to subtract plus minus, so it becomes minus plus. I'm trying to make sure that the correct points stay together. So when x is equal to positive 1 over the square root of 2, z is equal to 1 minus square root of 2, etc. So then the points on the ellipse are these guys. So then you just check all the points, and you find out that the farthest from the origin is this point right here. The minus square root of 2 over 2, minus square root of 2, and 1 plus square root of 2 is the farthest from the origin, about 6.83 units. And the closest to the origin are both of these points, 0, 1, 0, 1, 0, 0.